So and we are now recording our very first Zoom session, and I do this so that students who are unable to attend, because I think there's over 10 of you, but students who are working or whatever are able to tune in and they can at least listen to it as well. And what I'm going to be doing throughout these is sometimes sharing my screen so you can see what I'm looking at, my PowerPoint. Ah, we got another joiner here. That's good. Okay. Hello, Nicole. You haven't missed a thing. We just got started, just saying some introductions and stuff like that. So you haven't missed a darn thing. Where are you calling in from, Nicole?
Springfield, Missouri.
Oh, right there in the center. Okay. Yeah. We got someone here from Texas and a woman here from Minnesota and you from Missouri. So we've got a few. And my dad was originally from the state right between Minnesota and Missouri, namely Iowa. Insane and out wandering around. So I'm going to also say for not you people here who are watching live, but for those of you who tune into this, please do not look at these Zoom sessions through your cell phone. The cell phone is probably the worst way to look at these because I'm going to be showing graphs and it's just your screen is not going to be big enough to see very well. The Zoom sessions are much better seen, excuse me, on a laptop or a desktop computer with a regular size monitor so that you can actually see the stuff on there. This is normally the hardest course of your HIS program. Normally, this is the course that weeds people out because it has a little bit to do with numbers. Now, there you go.
That's my son.
As soon as I said numbers, the howl went. I was someone, hey, how are you? Look at this guy. How are you doing, cutie? Hey, look at me. I got glasses on. It's great.
That's my son, Roman.
Well, good for Roman. Good name. So here we go. A couple of things. These Zoom sessions are also not to be missed. I'm going to give you a secret here. 95% of your course content is in these sessions. If you don't watch them, you're screwed because your quizzes and midterm and final come directly from these Zoom sessions. When I share screen, I'm going to be talking to you from the notes. Now, I'm going to show you, let's share screen, and I'm going to go to where we are on my picture here. And let's see. Do you see this dashboard here? Can you see that now?
Yes.
So what I've done is I've gone into 110. Once I'm in good old 110, you'll see home and coursework. So I'm clicking under good old coursework. Once I'm in coursework, you'll see your units. Now the unit 1, if I take a look at that, I'm pulling it up here. All right. On unit 1, one should see at the very top, although I do not see the notes of it. Were you able to download? Oh, here they are. Look at the bottom.
Yeah,
notes in PowerPoint. Those are what I'm talking from. Now, some of these are in PDF, so don't worry about those. That's the Department of Redundancy department. Don't worry about them. The main thing you want is the notes and the PowerPoint. Always, always. I'm going to be showing you the PowerPoint and showing you the notes throughout the Zoom session. And then all of a sudden I'll stop sharing and then I'll start talking to you like this and explain, and you guys can ask questions and things like that. These Zoom sessions are about an hour in length, and they are an absolute must. They beat the crap out of looking at your textbooks or anything else because all the notes that you're seeing are taken from your textbooks. I've taught this course about 10 to 12 times already, and all the notes are kind of like a shrunken, condensed view of everything you're covering in the course. If I'm sharing screen again here, I'll pull up the notes and we'll see what we're talking about here. So you're looking at these guys here. You can see your pages here. There's probably 3 to 4 pages. I see 1, 2, and 3, 4. And I think that's going to be about it. There's about 4 pages. It's pretty densely packed. Okay,
Yeah.
if I make it a little larger, well, not that big. That's getting ridiculous. But at any rate, so as I talk through these notes, consider them your cheat sheets. I would always have these printed up before the Zoom sessions. Just go in 10 minutes before the Zoom session and print up the notes so that you've got them right in your hand so you can scroll down with pen or pencil on the notes, however way you like, while we're talking. At the same time, we also have a PowerPoint presentation, and this PowerPoint goes along with the notes. So sometimes I'll shift to the notes, I'll shift to the PowerPoint, but the PowerPoint always corresponds with the notes. In this course, I think Ms. Lynn Royer may have told you a few things about the way the course is set up. Has she done any of that last week? I think she did.
Yes, she did. Yes, she did.
Good. Okay. So what I'm going to do here is I've got something else I will show you on the screen here while I got you. Let's see. Okay. Basically, can you see this? Good.
Mm-hmm.
Now, if you take a look at this, you're going to see Units 1, Acoustics Frequency, PowerPoint, Acoustics Frequency. Okay, those are the notes in the PowerPoint that you have. In a couple of weeks, we're going to leave that section behind and go to Unit 2. And this is where we will cover intensity and the decibel. Later on, in a few weeks, we'll be looking at complex sounds instead of simple sounds. Now, a complex sound is like speech, music, trucks, traffic. Most sounds are complex. And we'll be talking about the unique thing about speech, because if you think about speech, that's what people want to hear with hearing aids. And when you think of the word speech, listen to how that sounds. Speech is... Most people lose hearing in the treble. They have trouble hearing treble. You're going to learn this in anatomy. You're going to learn this in every course you take in the Hearing Instrument Sciences program. Elderly people lose treble. When you can hear bass but not treble, this is what you hear like. I'm going to curl up a piece of paper. This is what you hear like. You just don't hear very well. You don't hear the high pitches of speech as much. Hearing aids literally try to amplify the high frequencies of speech. Now, what are the high frequencies? S, F, TH, as in church. So in the word speech, elderly people will hear the E. They won't hear the they can't hear treble. So that's why it's so important to cover acoustics, because if you're talking about hearing aids, you have to know what sound is. The first half of this course covers sound. So when you're looking at this here, the units 1, 2, and 3 cover sound. And then when you look under unit 4 and 5 and 6, you're going to see those called psychoacoustics. Now, this doesn't mean by sound by people who are psychotic and mad. This, I just swatted away a bug here. This means your perception of sound. So first we're covering the physics of sound. Later on, we'll cover the perceptions of sound. And I'll tell you why that's important. You go in for a hearing test. Let's call the guy Herb. Herb doesn't want to be there. His wife dragged him in. His wife says, "You can't hear me worth crap. You need a hearing test." Herb goes in, and this nice young woman is doing the hearing test on her. Herb is a macho farmer, doesn't want to be there in the first place. So the lady tells him, "Okay, raise your hand whenever you hear a tone. I'm going to give you tones in your right ear and then in your left ear, and I'm going to make them real soft. Let me know every time you hear them." Well, Herb is going to be, he doesn't want to make any mistake. He was dragged in there. He's going to make sure he hears that tone good and ready before he puts up his hand like, he doesn't want to be there. So he's going to hear the tone is loud enough for sure. Whereas here comes the kindergarten teacher. 72 years old. She used to teach 5-year-old kids, has her little white gloves and purse on her lap. She used to give tests. She doesn't want to fail a test either. So when you say raise your hand when you hear the tone, shoot, she's like a Las Vegas gambler. She's putting up her hand all the time. She's even putting up her hand when she's imagining she's hearing a tone. It's your attitudes and your perceptions coming into a hearing test that make a huge difference on the actual scores that are entered on your hearing test. This field is an art and a science. So you're going to learn part of the art and part of the science of testing hearing. You're going to become opticians, but for the ear. You're going to learn how to do hearing tests on young and old, but you will not learn to do hearing tests on babies or infants. That's the scope of the audiologist, someone with a master's degree, and now they have a doctoral degree. It's an AUD. Audiologists who study at Missouri State University or University of Minnesota or University of North Texas in Denton, just north of Dallas, they all get their AUDs. Now, they know how to do balance testing, brain waves of sound, infant testing, but they also test adults and fit adults with hearing aids. HISs like you all and me, we fit adults with hearing aids. We don't touch kids. Now, I'm an audiologist. I have a post-hole digger. I have a PhD. But I'm teaching the HIS program because I like teaching. It's more fun. So at any rate, so I'm an audiologist, but I jump ship and I train more HIPs than anything else. In Canada, we call them HIPs, hearing instrument practitioner. You guys call them hearing instrument specialists. Same thing, same thing. 2-year college diploma is what you're getting, or a degree, which is fantastic. Great. And it's not the minimal requirement. You're getting more than most people are getting. Most people take a 1-year distance ed course out of Detroit, Michigan, International Hearing Society. Anyway, this is just all introducing ourselves to each other, just talking and yakking. I haven't even delved into the course at all. I'm just yammering. Anybody got any questions? No, we're good to go. Cool. All right. So at any rate, this is your course in acoustics. It's a very good course to take along with 120 anatomy. I'll be teaching anatomy this afternoon. I guess it's at 3:30 Central Time. I'm on Pacific Time, so it'll be 1:30 my time. At any rate, and the courses are all interwoven and uniquely done the same way. In the anatomy course, it's the same thing. The units, there's 8 units. And in each unit, you're going to see a PowerPoint and notes. And in each week, you have a Zoom session. I encourage everybody never to use a cell phone to look at these because it's too darned small. And in that course, too, 95% of the content is in these Zoom sessions with these notes and PowerPoints. Usually, the structure of the course is there's 2 quizzes take place before the midterm. Quiz 1 and Quiz 2, I think they each have 10 to 20 questions, something like that. They're true, false, multiple choice, simple. If you've been in the Zoom sessions like these, you'll get them like snick or snack, no problem. The midterms are true, false, multiple choices, a couple of diagrams to label. Let's see what else I can lie to you about. Tell you about. And then between the midterm and final exam, you also have 2 quizzes. So there's a midterm, a final, and 4 quizzes throughout the course. That's what forms your grade for the course. Some people freak at this course because they think it's all numbers. It's not. There's no trigonometry. There's no math that way, calculus. I failed 10th, 11th, and 12th grade math. I had to go to summer school each year to do it, to pass. I am not a brainiac when it comes to math. The simple stuff you will have here is called arithmetic. It's going to take addition, subtraction, multiplication, and division. Usually everything's on base 10. Go ahead and use a calculator. I don't care. Doesn't matter, but that's as tough as it gets. Okay? Some people freak at it because, oh yeah, I'll say, so what's the average of these 3 numbers? And you need to be able to figure out an average. You add the 3 numbers up and you divide by 3, you'll get the average. But there are, believe it or not, some people who don't know that. So You know what I'm saying? Anyway, let's cut to the chase and get into the course a wee bit. What the hey? All right, I'll shut that guy down here. Here's a PowerPoint, and I'm going to blow up this guy right here, and we will talk about sound. Now, what you're looking at here is sound being made by a tuning fork. You'll see the tuning fork vibrating, and what you got to look at is these molecules of air. Now, sound is movement of molecules in air. When the tuning fork is vibrating, you are upsetting the natural order of molecules in the air. Normally, it's just Brownian motion. There's just molecules just moving all over the place. As soon as you strike something, you now are squeezing and separating. Squeezing and separating. Follow my cursor. You're condensing them and you're rarefying them. As the words say, compression or condensation and rarefaction, spreading them out. And that's what sound waves are. Sound waves are, they don't go up and down like this. I'll show you another slide. Here's another picture. Here's sound being made from some force. And notice how the molecules are spread out, squeezed together. Spread out, squeezed together. Here's another, oh, these are just, I'll look at that later. Here's another picture. Here are actual sound waves in air, okay, being made by some sound. Here's what we draw them like. And you know why we draw them like that? Because it's easier than going, who wants to do that? Okay, but sound waves don't go up and down, because if they did go up and down, we would be on a real acid trip. Our heads would go, hey, they don't do that. Okay, sound waves don't do that. We draw them like this because the up portion represents the squeezing together, the condensation. The down portion represents the rarefaction or spreading out. If these guys are really tight together, you've got a high frequency sound. If they are long and spread apart, in other words, if these black areas are like 2 feet wide and the white area is 2 feet wide, we have a low frequency sound. Okay? So high frequencies, the waves will be drawn like dee 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 dee. Follow my cursor, okay? Up and down. Low frequencies will be long and long sound waves. Now let's just kind of go to other waves. Light. I mean, look at this. AM radio waves. Shortwave radio wave. Television, FM. If we had AM, now we got FM. Microwaves. From your microwave in the kitchen. Okay? And finally, you get into visible light that we can see. Finally, infrared. And then look at this. Red. And then yellow, green. And then ultraviolet. And then you're out of the light range again. You can't see that anymore. And you're getting into gamma rays and X-rays. Those are all light types of waves. Those are not like sound waves. These waves can go through outer space. When you're looking at stars at night, you're only looking at visible light, this little narrow bandwidth, but there's stuff that's below what our eyeballs can see, and there's light waves that are above what our eyeballs can see. And those are picked up by telescopes around the world to talk about radio waves and blah, 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 and they start to discover the cosmos and the universe and all this crap. I mean, when you're talking light, I'll stop sharing. Light goes 186,000 miles per second. 108, so that's 6 trillion miles an hour. Sound, 766 miles an hour. So compare 6 trillion to 766. So light from the sun takes 8 minutes, here, that's it, 8 minutes to get here, to get to Earth. Light from the moon takes 3 seconds to get here. Light from the nearest star takes 4 years to get here. So when you're looking at the nearest star, that's 4 light years away. Typical stars that you're looking at, hundreds of light years away. Their light left that star hundreds of years ago in the time of Columbus and is now finally reaching your eyes. So light going 6 trillion miles an hour took that long to get here, so you can bet your bottom dollar stars are far away. Far away. Sound is a different kettle of fish. Look at the guy a block down the road who's pounding on something with a hammer. You can see the hammer going, but it's going. It's taking a while for the sound to get to you, and that's from a block away, because sound goes only 766 miles an hour. It's way slower. That's why you get an echo when you yell across the Grand Canyon. Hello, hello, hello. It took that long to go. Sound waves also cannot go through outer space. Sound waves need a medium. They need molecules to vibrate. That's why I showed you that tuning fork. In outer space, there is no air. So I could yell till the cows come home, and you're not going to hear a word I'm saying. Sound goes through air, it goes through water, it goes through steel. And when you think of water, if you have your head underwater, and I click 2 rocks under the water, sound goes 4 times as fast through water than it does through air. Sound goes through a railroad track, steel, 14 times as fast as it does through air. That's why First Nations people used to put their ear to the ground to listen for the buffalo coming. You can hear through the ground way sooner or way quicker than through the air. That's where the saying comes from, I'll put my ear to the ground. Oh, I'm looking for a job. Okay, I'll put my ear to the ground if I'll let you know if I hear anything. Okay? Sound going through air or through solids goes much faster than it does through water, and water sound travels much faster than it does through air. Let's share the screen again. Isn't that special? And we'll see if I can get off of this particular picture, because this PowerPoint gets to be a little bit weird at times. Okay, good. Now I can escape, I can shrink that puppy, I can pull up this guy here and look at our notes. Your readings in this course for next week and all that stuff, what we're looking at here is sinusoids. The topic is frequency period. We'll talk about wavelengths of sound. We'll talk more about the speed of sound. We'll talk about sound fields. Now look at this, sound fields. That has nothing to do with a football field. But a sound field is any place where sound takes place. In a room, a gymnasium, outside. We'll talk about resonance. Now, you take a wine glass at Christmas, and you lick it, your finger, and you... Do you know why your ear has this shape? Your ear has this shape because, like this cup, we'll stop sharing screen here again. You're going to be so sick of me. See this cup here? This cup here is actually from Auburn University in Auburn, Alabama, y'all. I used to teach there. Anyway, if this was a wine glass and I made it resonate, vibrate, your ear is also a resonator. Your ear canal is 1 inch long, and your ear has these little bumps and ridges because it has to. Do you know why you have that? Because your ear naturally resonates with, guess what? Treble. And what are the most important sounds of speech to hear? Treble. Because that's where the consonants are. Think of the word sat, hat, fat, bat, ca. They all have ah, but what makes them different is the consonants. So you have only 5 vowels, and every word in the English language has 1 or more of those vowels. So vowels don't tell you squat about what word was said. Did they say kittens or mittens, dishes or fishes? Okay? It's the high-pitched consonants that you make with your lips and tongue. That tells you what the word was. So your ear has that shape because we speak. If we didn't speak, our ears wouldn't be shaped like that. Isn't that weird? We'd have dog or cat's ears. My phone out here is just ringing away, but I just can't be bothered. This is more important. So anyway, so now we're talking in our notes here. In this course, we will cover physical properties of sound, acoustics. Physically, sound is a propagated change in the density of an elastic medium. Now, there's a statement for you. Check that out. Sound is a propagated, in English, that means forced. You did something. You clapped your hands, struck a tuning fork, talked, okay? You did something, okay? So it doesn't just come out of nowhere, in other words. And it's a propagated change in the density. What do we mean by that? Well, here's the density. Let's go to the PowerPoint here. Look. The density of this medium, you've made a propagated change. I hit the tuning fork, and it made changes in the density of the medium. Okay? A propagated change in the density of an elastic medium. Elastic medium just means a medium that doesn't want to be disturbed, but you did disturb it. Okay? Sound is a propagated change in the density of an elastic medium. Could be air, could be water, could be steel, doesn't matter. So I will ask you this. If a tree falls in the woods and nobody is there to hear it, is there a sound? Yes or no? Tree falls in the woods and nobody's there. Is there a sound? Yay or nay? What do you think?
I think there's still a sound, but nobody's there to hear it.
Correct. Sound is a propagated change in the density of an elastic medium. So nobody was there to hear that, but nonetheless, according to the definition of sound, did the tree falling in the woods make sound waves in the air? Yep. Sound is. Can't help it, but there it is. All right, share screen again. Back to the notes. Psychological perception of sound is your psychoacoustics, and that's what I was talking about earlier. It's the act of hearing. Sound is an auditory experience. The anatomy, physiology of the ear is covered in your anatomy course. Your anatomy of the ear sits right between the physics of sound and your perception of sound. Now, if you're looking at this, here's the slide here, simple wave motion in air. Brownian motion, circle that word, that's just random air molecules moving. That's air molecules moving without a sound. Random movement. Propagation, the next little heading means strike a tuning fork. Something has to cause or propagate, cause an abrupt change in the random Brownian motion of molecules. Inertia, forget that, blah, 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 blah. The tuning fork just kind of goes, it doesn't want to move, inertia means it pulls back, all that kind of stuff. Not to worry. This is the important one right here. Sound waves, a series of squeezed, condensed, and then spread out, rarefacted molecules. Remember that one, faux show. All right, here we go. Let's see. There are, where was I here? Make sure I'm on track. Okay. Yes. Make that a little bit smaller. Just a wee bit smaller here, so you can, oh yeah, boy, Ted, you're overshooting here. Get your glasses on so you can even see. Okay, now read with me just what we had here. There you go. This part right here. Sound waves, longitudinal or transverse? Transverse, this is important, so put a star by this. Transverse waves are like waves on water. Water waves, waves that go up and down. See, the wave may be moving toward the shore, but the wave is also going up and down, isn't it? Water waves are transverse waves. The molecular motion is perpendicular to the direction of the wave. The wave may be coming into shore, but the wave is also going up and down. Water waves. Longitudinal waves are sound waves. Molecular motion is in the same direction as the wave. Here, look at this. The wave is squeezing this way, and the direction is also moving that way. It's not going like that. Remember, we draw sound waves up and down just because it's easier. These are transverse waves. This would be longitudinal waves. So never confuse the two. Water really moves like this, as you know. Sound waves really look like this, but we draw them like this because it's easier. Longitudinal, there you go. You'd think I wrote this. We draw sound waves like up and down bumps because it's way easier than drawing dots of molecules bunched together and spread apart. Another thing you're always going to encounter in your readings is some word called sine waves. Sine, S-I-N-E. Well, think of the word sinus. Sinuses. Behind your nose are all these curved passageways. Sine in Latin just means curved. Okay? So sound waves. And degrees of phase. Okay, let's see if we go here. This is just giving you introduction. Don't freak. Don't freak. So here you go. Here's a picture of a speaker. Whoa, wrong. There you go. A speaker and a speaker. And this speaker's making a low-pitched sound. It's moving back and forth slowly. So it's got a big rarefaction, a big condensation, big rarefaction, big condensation, and we draw it like this. This speaker is making a high-pitched sound. Narrower condensation, narrower rarefaction, condensation, rarefaction, condensation, rarefaction. In the same length of time, look at this, distance or time, you've got more condensations. Condensations are always drawn by the up on the wave. Rarefactions are always drawn by the down of the wave. This is a low frequency sound or a bass sound. This is a high frequency sound or a high pitched sound. Okay? Up over to here. Now, look at the circle on the left. A circle has 360 degrees. If you're doing a 360 in the parking lot, okay, start at 0 to 90 to 270, all the way back up to 360 again. Okay, here they're starting at 0 to 90 to 180 to 270, back to 0 again, 360 degrees. Well, a sound wave can be seen as the same thing. 0 degrees phase, 90, 180, 270, 360. And now you're back to 0 again. In other words, if you took the bottom part here and turned it around, you'd have a big circle. So just like a circle has 360 degrees, a sound wave has 360 degrees. So by the time you get to 360, you're back where you started again. Got it? So here you go. Here's 0 phase, 90 degrees, 180, 270, 360. You're back where you started. So call this 0, 90, 180, 270, 360 again. Now you're back at 0. So how many waves do you see here? Well, I see 1, 2, 3.5. About 3.5, sort of, kind of. I see 4 condensations and about 3 rarefactions, so about 3.5 waves. Here I see, if I'm starting here, where do I end up getting back to here? I guess over here. This one only has like 1.5. It's a much lower pitched wave, lower frequency. This is showing you another picture of phase. Okay, just have a look at it and now you're seeing it directly. 0 degrees phase, 90, 180, 270, back to where you started. Denotation of a sine wave into 360 degrees. Look, this is one single cycle of an ongoing sound. Okay, here, let's see. Here, This is all we did was draw one single cycle, another cycle, and another single cycle. That's all we're doing. So all this is showing you is just one complete wavelength. And then it would begin again, complete wavelength. Here you're showing now this wave's beginning at a totally different phase. This wave decided to start as a rarefaction. Well, and then it went condensation, and now it's rare condensation here. It just doesn't matter. I mean, shoot, look at the speaker here. This speaker started rarefacting and then condensed, rarefaction, condensed. This speaker started condensed. Whatever, doesn't matter. The point is, this is one wavelength, that's one wavelength. What is a wavelength? Time on the horizontal, time and amplitude. Amplitude over time. Amplitude, time. Always, always, this is another star, okay? When you're showing sound waves, time is on the horizontal, amplitude is the vertical. Always, always, always. Look at this weird sound wave. Look at this one. It started way over here, went all the way down, and now you're back to where you started. So if this is 0 degrees, this would be 90, this would be 180, this would be 270, back to 360 again. Whatever, doesn't matter. Okay, big hairy deal. Now, there are 3 dimensions to sound. Frequency, intensity, and time. Sound can be bass or treble. Sound can be loud or soft. And it's also the phase. When did it start? So let's look at the top one. Look at 2 sounds. Look at these top 2 sounds here. How are they different from each other? Are they different in their intensity? Yay or nay? What do you think? Tell me true. The top one. Is the amplitude any different between these 2 sounds? No. Ramirez is right. There's no difference. So they're different in frequency, because this sound wave has way more waves in it, whereas this one here has less. So this one's a low frequency wave where I'm drawing my cursor, and this one is a higher frequency wave, but they're just as loud as each other. Look at the middle 2. The middle ones, are they the same in intensity? Yay or nay? Talk to me.
Yeah.
I agree, they are. Are they the same in frequency? Yes or no?
Mm.
I think so.
I think so. There's the same amount of bumps, really, essentially. How are they different? They're different a little bit in phase. They began slightly different. They began at a slightly different degrees. That's all. Otherwise, they're the same loudness, same pitch.
Okay.
Look at the bottom pair of sounds. Are these the same in frequency?
Mm-mm.
Yeah, they are.
Are they?
There's the same amount of bumps. 1,
Okay.
2, 3, 4. Same frequency, identical. Are they the same phase? Yep, they began right there. Look at this. They began at the same phase. No difference. How are they different? In amplitude, the height. Remember,
Okay.
time is on the horizontal, amplitude is the vertical. So it's an important picture because it shows you how 2 sounds differing in frequency, 2 sounds differing in time, and 2 sounds differing in intensity. Here's another picture showing you the same thing. This one's a little easier to read. This one's in one of your textbooks, actually. Look at the top pair of sounds. You see how are they the same frequency? What do you think? The top pair.
Yeah.
Yeah, correct. Look at the bottom pair.
No.
No. The bottom, or I should say the middle pair. The middle pair are the same in amplitude. They're just as tall as each other. The top pair are the same in frequency, but the bottom one here is way smaller in amplitude. So the top pair, they're the same in pitch. They might be both bass or they might be both treble or whatever, but this top one is loud and this one's soft. Look at the middle panel. They're the same loudness because they've got the same height, but this one has way more bumps than this one does. So the one with more bumps is a higher pitched one. It has shorter condensations, shorter rarefactions, shorter condensations, shorter rarefactions. Look at the bottom pair. Are they the same in frequency or in pitch? Do you see the same amount of bumps in both of these bottom waves? I do. Are they the same in amplitude or in height? What do you think? Yeah. How are they different?
High and low is what I noticed.
Well, they're the same in height, so there's the same amplitude, the same loudness. They have the same amount of bumps, so they're the same pitch. They might be both bass, or they might be both frequency or whatever, but they began at different phases. Now, I'm going to tell you why this one kind of is important. Designers who make auditoriums, okay? Like if you're making an auditorium where plays are going to be held, or concerts or symphonies or whatever, they have to design theaters really carefully, because sometimes the sound wave coming from the speaker may come to the audience, but there may be an echo back that's opposite in phase. And if that happens, these two sounds cancel each other out. You have the sound of one hand clapping. You've got a dead spot in the room. So again, these two sounds differ in intensity. These two differ in frequency only. These two differ only in terms of phase. If these two were played at the same time, they'd cancel each other out completely. Let's see where we are in our good old notes now. Okay, we can even read where we were here. Note, and we got about another 15 minutes and then we're done here. You guys this is good. This is just take your medicine. It's okay. We're all good. We're going to spend a couple of weeks on this stuff, so no worries. Don't freak. Okay, it gets better. Now, note the axes of the diagrams again. X, the horizontal is always time on a sound wave. The vertical axis is always amplitude. Okay? And I'm going to show you what I mean here. Look at this. I'll show you in just good old plain English. The height of the wave, where it says amplitude here, okay? In terms of what I was showing you with that tuning fork, it would mean if this was a really tall wave, it would mean that these molecules were really squeezed together. And these white molecules, they would be really spread apart. In other words, the black versus white would be extremely obvious. Whereas if it was a very soft sound where the amplitude wasn't very high, this gray area would be hardly any more gray than this white area would be. There would be kind of dark gray to light gray to dark gray to light gray. If the sound amplitude is large, you're going to have black, white, just really tightly squeezed, really far separated. I mean, really like, so I guess that's kind of what I'm trying to get at here. I'm trying to show you the transition between sound waves in air versus how we draw them. And we're just getting introduced to this. This whole area here, think of sound as a circle, blah, blah, blah. You got 360 degrees, blah, blah, blah. All the rest of this stuff, ignore. Don't even think about it. It's there for nerds. You can read it if you want to. See why the Zoom sessions are important? Can tell you what you need to pay attention to and what you don't need to. Next. Here you go. 2 ways to represent sound. 2 ways. We've shown you one way. And one way is in good old sound waves. Let's see if I can show you the other way. The other way to represent sound is this way. A spectrum. A spectrum doesn't show you sound waves at all. A spectrum shows you it's got this many sound waves per second, and it's showing you another sound, and another one, and another one. I guess what I can say is this. If you think of sound as a loaf of bread, if you take a slice out of the bread and you turn it this way so you can see the raisins, that's a spectrum. If you take my speech my talking. It's a complex sound. It's got a whole bunch of different sound waves in it. Not only does it have bass, but it's got treble and mids. It's got all different kinds of sound waves in it. So a spectrum is showing you all the different sound waves in it. And this line here means there's 100 bumps per second. And this one here means there's another sound wave with 200 bumps per second. And this one here, a third sound wave of 300 bumps per second. So you can see there's a lower pitched, middle pitched, and higher pitched sounds. And you can also see that the lower pitched sounds in this example, this is just an example, are also the greatest in amplitude. And the higher pitched sounds get lesser and lesser in amplitude. So sound waves are one way to show sound. A sound spectrum shows you what pitches are in the sound. And when you think of a spectrum, memorize this. Frequency means the number of cycles per second, okay, is always on the horizontal. Amplitude, just like in sound waves, is always on the vertical. Frequency is always the horizontal. Amplitude is always the vertical. And let's talk about frequency so that you get the word frequency. Just look at the word frequency here, where I'm highlighting. Frequency means the pitch. Frequency can be used to describe anything. How many footsteps per second? Oh, 2 or 3. Okay, that's the frequency. What's the frequency of the tick-tocking of the clock? Tick-tock, tick-tock, I guess 1 per second, because tick-tock, tick-tock, 1 per second. Frequency is how many times something happens per second. Okay? In sound, frequency means how many cycles took place in a second. How many cycles took place? If it's a low-pitched sound, not very many. If it's a high-pitched sound, as they'd say in Louisiana, beaucoup. Okay, you've got lots. So I'm going to show you here, if we can, high and low frequency. Here you go. Here's a picture. What the hey, look at this one. Here's time, here's time, here's time. This wave, only 1 cycle took place in this unit of time. This wave here, 3 cycles took place in the same unit of time. In this, call this a second, from here to here. In this sound, lots of waves took place in that 1 second. So go back to the left. 1 second from my cursor here to here. 1 second from my cursor here to here. 1 second from my cursor here to here. In this first example on the left, 1 cycle took place per second. In the middle one, 3 cycles took place per second. And in this wave, probably like 10 took place per second. And in sound waves, instead of saying cycles per second, we say hertz. Just like Hertz Rent-A-Car. H-E-R-T-Z. Hertz. Hertz. This cycle here, this sound would be 1 hertz. This middle one would be 3 hertz. This rightmost one would probably be like 10 hertz. Okay? That means it really hurts. No, it just means there's 10 cycles per second. If we go up one, so you got, there you go. Okay. All right, back to your notes here. Let's see what we can lie to you about here. So hertz. 1 hertz equals 1 cycle per second. For example, a sound with a frequency of 100 cycles per second is 100 hertz. Okay? Now, just to let you know, humans, we can hear sounds as low as 20 cycles per second. That's the lowest pitch we can barely hear. The highest pitch we can possibly hear is 20,000 cycles per second. So the range of our hearing is from 20 hertz to 20,000 hertz. Okay? And we lose the high-pitched treble hearing sensitivity each decade of our lives. By the time you hit 65, you can only hear from 20 hertz to about 4,000 cycles, 4,000 hertz. Okay, so we lose 20,000 by the time we're 10. We lose 15,000 by the time we're 20. We lose 14,000 by the time we're 30, and so on. All right, it's just that it's really kind of interesting that way. I'll tell you a little story here, just to lighten the load. There's a guy in England. He developed something called the mosquito. He didn't like teenagers hanging around his drugstore. It really pissed him off. You know, they'd be out there with their rap music and their BMX bikes and stuff like that, and he didn't want them hanging around his drugstore. So he made something called the mosquito. It was a speaker that emitted a 15,000 hertz tone. It's a really high-pitched tone. The teenagers could hear it. They hated it. They'd be around there. They'd be going, "Oh my God, it makes the back of my teeth, I can feel, oh, let's get out of here. Ah!" The adults couldn't hear it. The effectiveness was seen by the sudden disappearance of teenagers hanging around his drugstore. I think it's diabolical. Anybody who can come up with something like that, the mind that comes up with something like that, I wish I had that. I just think it's hilarious. But it drives home a point. We lose high-pitch hearing through the decades of our lives. The range of human hearing is from 20 cycles or 20 hertz, 20 cycles per second, to 20,000 cycles per second, 20,000 hertz. By the time you're 65, you can hear from 20 to about sometimes 2,000, maybe 4,000 hertz. And when that happens, you can't hear the consonants of speech, because the consonants of speech are 4,000 hertz. When you lose 4,000 hertz, hey buddy, you got to see someone's face to tell what they're saying. You're using your hearing aids constantly. So yeah, that's why elderly people say, "Oh, you young kids mumble." Kids mumble today. Well, that's because they can't hear the high-pitched consonants. So if I'm talking like that all the time, how are you going to hear all the time? So I mean, if I'm talking into a horn again, and I'm going to do that just to give an example. If I'm doing this, and at the same time, if I'm talking like this, now you're only hearing the low-pitched bass of my voice, okay? You're not hearing much of the high pitches. And then I start making background noise like this, you're going to have a hell of a time hearing what I'm saying. Okay? Hearing aids try to take that sound and turn it upside down. When I talk to you through a horn like this, my consonants are emphasized. You can hear that even better. Now that's just physics. Hearing aids aren't really like horns, okay? But I'm just giving you an acoustic example. Most hearing aids today do deliberately amplify treble on purpose. They're high-pitched amplifiers. So when you see these devices advertised in the back of magazines for 25 bucks that elderly people want to buy because they can't afford hearing aids, those amplify bass. It's easy to amplify bass, but they've got good bass hearing to boot, so that's not going to help them. They're going to hear the bass louder than they already do, and that's not it. They need treble. They've got trouble hearing treble. So anyway, this has been our first little yammering talk on acoustics. We will continue, next week, same time, same channel, and we'll continue on about frequency and period. I want you to read your notes and read your readings quite carefully. And the notes, what we did from here, if I share screen again, especially, I mean, if this was like a 2-hour thing, God forbid, we're going to get into something called period. And when you're looking at period just means here's the amplitude, the height. Period means what's the length of time it took to complete one cycle of sound. What was the length of time? Period is the length of time. When you hear the word period, think your watch. What time, okay? And it's always per second. But how many wavelengths took place in 1 second? 1. So what was the time it took to complete one cycle? In this example, 1 second. Okay? Because the time to complete one whole 360 degrees was 1 second. If you go to here, to get from 0 to 90 to 180 to 270 back to 360, if this was 1 second, the period would be, or the frequency would be 1 hertz. So basically what I'm trying to tell you is they are inversely related. Look what it says here. I'm just going to leave you with that to ponder, okay? Period. The time it takes to complete one cycle of a sound. For example, e.g., it says here, if a sound is 1 hertz, then its period is 1 second. If a sound is 100 hertz, if 100 waves took place in 1 second, then it would mean that one wave took 1/100th of a second. And that's what it says here. If a sound is 100 hertz, it means 100 waves took place over that same 1 second. That would mean the time it took to complete one of its wavelengths was 1/100th of a second. So frequency and period are inversely related. As frequency is increased, you're getting treble. Okay, treble means higher frequency. From now on, we're going to leave bass and treble alone. Those are psychoacoustics terms. We got to focus on frequency. Low frequency means bass. High frequency means treble. So as frequency is increased, the period is decreased, and vice versa. Frequency equals 1 over the period. Period equals 1 over the frequency. Put that in your pipe and smoke it, okay? Have a read on that in your readings. We'll come back to this next week. We'll start right here where we left off. Here, look where you can see where it says humans can hear from 20 to 20,000 hertz. Okay? La-di-da-di-da. Oh, yeah, look at this. Hearing tests. When people do hearing tests, we don't test up to 20,000 hertz. We test basically from 125 hertz to 8,000 hertz. That's where all of speech lies in. And by the way, BTW, 125 hertz is low C on a piano. 250 hertz is middle C on a piano. 500 hertz is high C on a piano. So the lowest 3 frequencies we test are 125, 250, 500, and then we test 1,000, 2,000, 4,000, and 8,000 octaves. We'll get to that next week. Not a problem. Anyway, it has been a slice. Live long and prosper. Be like Spock on Star Trek from many moons ago. Y'all be cool. All right?
All right.
Anybody got any questions? While we're here, if you want to, if something's kind of bugging you or pissing you off, something that you didn't quite get that I was talking about, ask. Go ahead. See, that's why this is an active online program. That's why it's better. It's more better because we can actually talk. So if you have questions, ask. I can stay here for another half hour. No problem. I'm good. So it's up to you. And if something's not clear, feel free to ask or email me. And my email, I'll give you my email address, okay? My email address, I'm going to write it down here so that it's actually seen. At otc.edu. Okay. Here, can you read that puppy? Tvenema, Tvenema, at otc.edu. Okay? Got any? Oh, actually, I'm lying. It's Venema T. It's Venemat. That's what it is. Venema T. That's what it is. I lied. Okay, VENEMAT at otc.edu. Okay, I know I made that. That's so. If something pops into your mind, you got a question. I will also give you my phone number, just to bug you. Okay, you can call me on my. Let's see, I have a cell phone and a landline. I'm trying to figure out which is the best one to give. I'll give you my cell phone number here. I think I can, you know what? I think I get charged on that. Call me on my landline. 778-433-9707. So if people have questions that come up, Email is best because it won't bug my wife quite as much getting all the phone calls. But nonetheless, I'm here to help. I want people to get it. And that's my main concern. I want to be as clear as possible. I always try to explain in a way that I wish someone had explained to me. So that's my motto. So I'm here to help, not to confuse. Don't want to make things oddly complicated, but it is important to do your part by making sure you read the stuff and always attend these darn Zoom sessions. This has been good. All right.
Is this our book?
Dictionary of Audiology.
Yeah.
I don't know if that you can use that one, but I don't think that's your book for this course. I think your book for this course is that one. That's Hearing Science Fundamentals, and that's the best book. That is a great book. Yep. Cool. And I think you also might have another text called Introduction to Audiology by F. Martin. Yeah, that's it. That book and the Hearing Science Fundamentals go together. Okay. So, and I think when I showed you my when I showed you the notes at the very top, I think they were from both of those textbooks, I believe. Yeah. Read Lassen Woodford. That's the one from. That's the one I would read for this time. Okay, the Hearing Science Fundamentals.
Okay.
All right. Tell Roman he's cool, and we'll see you when we look at you.
All right.
All right. Ciao.
Thank you.